Do we have sound? Yep, we're live from downtown Mill Bay. And oh, there we go.
They're not gonna go close to each other. We need one in Beyblade arenas where they're like.
Excellent.
Two people.
Of the toys.
Oh, there we go.
There it is.
Which one is that?
That's
Is that yours?
mine. That's mine.
Oh, rats. Wait, hold on. No, this might be making last time last green pop. Then we'll spin the green ball and the ball. So we spin it back.
Yep.
Two people.
There was a
Wait, last class? That's
Oh, mine's heavy.
One second.
skeleton notes.
Sorry?
was there new skeleton notes last class that got handed out?
Yes. Yep. Anybody else miss notes last day? Okay, put away the molecules, please. Put them in the tray. Get the tray up here. And I think I am missing part of this, but we'll start off anyway. We used to do this in the classroom where we'd build a wall of desks and you throw paper over top.
What?
Well, nobody cared about the desks in the rocks because they were old. I figured if I did that in here, occasionally it would collapse. If I so much as smudge a window, I think someone may come down and smite me.
I think if a desk collapses, it's not gonna smudge a window, it's just gonna break.
It might break the desk, but like we were told, oh, you can write on the glass to like do things. No, because if you write on this,
Oh.
I'd be in trouble because this will keep the ink and will be a little smudge. I think it's so that people don't walk into it.
Yeah, already.
Yeah. So it's a safety feature. So we now did the chemistry. I have to change it now that we've changed the demo. It's the chemistry net of science. And perfect. Create a pen. So we did a variety of different conditions in our model. What is the net representing? Yeah, because we have a reaction in which we start off with the reactants. It has to go over up to the activated complex and it has to come down. When we were all both on equal sides, would it look like this? No. So it's not quite realistic because most of it, where should that end up?
In line with it?
Yeah, it should be it's the same side, which is not it. But when I had one group, like you had to sit on the floor and the other side didn't, or no, I think I had you move farther away, then that starts to mimic more of a realistic reaction. And this is intended to show how an equilibrium affects the number of molecules and whether or not it's at equilibrium. So we started off all on one side, all on the other side, and I've got some different conditions and I've got some numbers. So we had the reactants and the products, whoops, and we had time, and at the very beginning we put there was 14 and there was 0 and that was times 0. After about 30 seconds, what would you guess those numbers would be? 7 and 7. I don't know what happens in terms of the law of conservation of matter, but it was like, first we had 6 and 8, which, it's close to 7 and 7. But then we had 5 and 5. So we're going to ignore the fact that matter seems to be disappearing. But the ratio is important. In this particular one, does it matter that we all started at one side? If we were to go beyond 1 minute, and I say put it forth in the future at 1 year, and I was like, you were playing volleyball for the rest of your life, crawling across the floor, we feed you there, but you're not allowed to leave. What would you expect the ratio to be? 5 and 5. Or maybe one will reappear, 6 and 6, but we would expect that ratio to go on and on and on and on. So this particular equilibrium, because it's a little fake, because our reaction looks like this, potential energy, reaction coordinates, there's an equal hump on either side. And so it's going to end up even out. But it doesn't matter what started, or does it? So then we did the opposite. That's all right. Should I stick on this page for anyone? Okay. Then I had I might run out of pages because I doubled up on one of them. I'm going to go back here and just write in also did all on product. Because when I did it again, I counted, we threw all to the other side, and we had like, I think it was 13, 0, we had lost one, and then we ended up with a similar ratio. It was 6 and 7, and then I think it was 7 and 7. So it didn't matter if we started all on this side, it didn't matter if we started on that side, we ended up with the same ratio over time.
If we're all on one side, why?
Oh, sorry, not you all on one side. The balls started off on one side. But that didn't change the number of people on the other side, so eventually the ratio became the same. Would it matter how many balls I gave you eventually for the ratio? Like instead, we started with 14. What if I gave you, I don't know, 100? How many would you expect on each side? 50. Because, I mean, there's more to throw, but you're just going to keep throwing until it evens out. We started with an equal number on both sides. We had 7 and 6 by this point. We had lost a couple. Time, reactant, product. 0 seconds, 30 seconds, 1 minute. And then it was 6 and 6. And then at one point it became 8 and 6, and 2 balls reappeared. But when we're dealing with individual atoms in this case, we're not going to get perfect ratios. But we would probably expect what ratio if we did it for 100 years? 1 to 1. I mean, by that time it would be your children playing, but you know. And then we totally cheated. And we had, we're not going to call it record, we had 12 people, I believe, and 3 people. Time, 0 seconds. We started off with 12 and 0. Would we expect the same 1-to-1 ratio? No. 30 seconds. It became 3 and 9. And at 1 minute, it was 2 and 8. Again, matter shouldn't disappear. 1 minute 30, it was 3 and 7. But again, if I put 1 year down, we expect that ratio to change. What is the ratio for these ones? 1-to-1. And we've already said that it wouldn't change if I increased the number of balls. The ratio would stay the same, even if the amount differed. We can actually calculate that. We could call that's a constant. And if I just said, let's put products over reactants, so the number doesn't matter, we're eventually going to get 1. That would be true of any game you played where you have equal number of people of skill and talent on both sides. We're going to expect a 1-to-1 ratio, roughly the same amount. But if I put a lot of people on one side, then if I work out this ratio, we have a constant, which obviously starts with a K. What would this ratio be? If I calculated it the same way as before, products over reactants. Pardon? 1 to 4, yes, but as a number. 4. You said 1 to 4, that's a quarter. And then you said 4, which is the other way around. Which one is it? I'm going to fix it so it's products over reactants. And why don't I arbitrarily say it, and I'll keep it consistent. These are reactants, and these are products. And so that would make it would be calculate one of them. What number do I put on top? 7. 7 over 3 equals 2. What? 2.333. And what's 9 over 3? 3. And what is? What's 8 over 2? 4. So we're obviously not accurate to two significant figures. So if we know that it's going to be somewhere in there, but it's 3, 4, and 2.3, what would be a good rough estimate for it? 3. 3 sounds good. Which makes a lot of sense, given that 1/4 of the people are on one side, and it looks like, well, actually 4 times more people on the other side. And we would expect that ratio to continue forever. So it's a different ratio, but the equilibrium is still going. Why can't one group overpower the weaker group, the one that has less people? What eventually happens if you have lots of people throwing the balls over top? Pardon?
You get tired.
You do get tired. But when you had lots of people on one side, the people that were on that side, were you able to grab a ball every second? No. Where the people there are 3 people on the other side, were you able to grab a ball every second? So what eventually happens to this side? What about?
Slows down.
It slows down. Why does it slow down? Because it does. What?
There's not enough product to use.
There's not enough product to use. If I'm going to go all the way back to here, so when I totally cheated and I put everybody over here, then like in the first volley, they fire things back, and then what happens? What do these 3 people do?
We're constantly throwing balls over. Like,
But-
we're constantly throwing balls over.
You're constantly, so you're 3. Whoa. It's all right. I didn't know that was even a thing. 3, 3. And then they've got, what are they immediately going to do? They're going to throw them back. They have so many people there. And then while they're doing that, they're going to throw 3 over. At no point can this side win, because no matter what they do, eventually they just run out of ammunition. They have all the ammunition. And so it's going to end up in a ratio. Probably most of the things are going to end up on this side, because they're always going to be able to throw it back. But in that ratio, it's still going to stay constant, and you can never quite overpower it, because you just run out of ammunition. Eventually, they're just waiting for them to throw it back. And once they throw it back, you have more ammunition. Now we sat on the floor, moved you up. This was to give you the what it would be like to have an inhibitor or a poison. I'm not entirely sure that worked out well, because I also moved you closer, because then I got a little worried. Those of you that play volleyball, is it possible to have two nets? Up and down? Like, can you physically? No, just that's just a dumb question. Okay, because if I asked Drew, sorry, Mr. Langer, he wouldn't agree to that. No, okay. We actually started off in this case with equal numbers. So this was when they were sitting on the floor. We had 7 and 6. What would you expect the next numbers to be? Different, same, continuous?
Pretty much the same.
Pretty much the same. Did the presence of an inhibitor affect the 1-to-1 ratio we had before? No, they're the same distance apart. We still had the same level. So if we're doing that, we actually ended up roughly the same, 5 to 4. And then it was, one was weird. I just don't think I can count. The next one was 5 to 5. There was a moment where I counted 5 and 3, but that means 2 of them completely disappeared. They're probably just in someone's hands. And so a poison doesn't affect an equilibrium. It just slows the reaction down. But since it's slowed down equally for both sides, you don't get a change in equilibrium. Now, the only thing about this that, again, makes it artificial is most K values for an equation, which are products over reactants, aren't 1. They're unequal to 1. But you could get one that was 1. It just means it's equal on both sides. It's very rare, but it could happen. And then the last one, okay if I move on? When I built the wall of chemistry, we would cover up the holes with aprons. And then we would take down the aprons and say a catalyst. And I didn't know how to do a catalyst in the particular ones, and I didn't want anybody to hurt themselves. I'd already had a ball to the face myself, so I wasn't going to have you like whip it at each other. But I fed you all Red Bull, 3 coffees, maybe a little meth, and then you're that would be catalyst. You're going a lot faster. But what we did instead is we sat further apart. So the sat further was here. And that was to re-demonstrate more of a proper curve. No, 30 seconds. Now, just knowing what you know from being in there, which side should have the larger number? Well, we started off with 6 and 5. Which side, where should all the balls end up on? Further, because they can't throw it back as fast. So they're farther back, it takes more effort, they're not getting it as well. And so it did end up very quickly. This was 8 and 3. And then it was 2 and 9. And then I think we ended up, 9 and 4. 2 reappeared at some point. And so we end up, but again, if you could calculate a ratio for this, products over reactants, given the numbers here, what would we expect the ratio to be? 1 to 10 might be a little high, but I don't want it in a fraction. I want it in a decimal. Products over reactants. How many of you in your calculators, when you calculate something, and then you get like an answer that's like, I don't know, I saw someone do something like this, and they said it's 7/43 moles. How many of you get fractions from your calculator? Never use that. Those aren't real. Fractions don't exist. They're just a number. And that number has significant figures. But mathematicians like to pretend don't exist. I like to scare Ms. Walensky with significant figures. What would that be as a number? Pardon?
4.5.
4.5. Sure, probably. Oh, you gave me another fraction. 4.5. Yeah. Now we're dealing with individual molecules, so there's little bits of changing. But if we were dealing with millions and millions of molecules, you'd probably get a fairly steady number. Would we expect that number to change over time? If I went for like a minute 30, 2 minutes? Yep.
Does the ratio like change?
Does the ratio
How do
change?
you know it's done?
Oh, yeah. Does the ratio ever change?
No.
Like throughout the table.
Yeah, like a,
Well,
Would you just average the ratios?
Well, one of the things that we're dealing with 11 volleyballs, or 14 to start with, they seem to disappear half the time. And we're just counting individual atoms. But if we were to keep doing this, like if I flip 11 coins in a row, or 14 coins, then will I always get a perfect 50-50 ratio of heads to tails? No. But if I did it with 1,000, would you expect a pretty close ratio to 50-50? So in this case, if we did this with 1,000 volleyballs, would we expect a constant ratio?
but what ratio
How
do
do
you use?
Yeah, how do we get that?
Oh, and when we do it with, don't worry about that in the sense that when we do it with real molecules, you're going to get the ratio, like in moles. Because it's number of volleyballs, we don't use number of atoms, we use moles of atoms. So the numbers will be large.
Like when it's moving back and forth,
Yeah.
is it this singular atom that's moving, or if you have like Cl2, it's moving? bonded?
So when it's moving, this is a really good question. When it's moving back and forth, what is it doing? So in the process of the volleyball, I like this one because this is the best one in terms of, we've got sits closer. So if this is this one, which one represents sat closer, left or right? Jeez, my microphone now did something. Sat closer. And the reason this represents it well is because do they have to throw as high? No, it's less energy. Whereas this side has to throw a lot harder. So that's like sitting further away. So over time, where are all the volleyballs going to end up? They're going to accumulate here because it takes them longer. But they're not going to have ammunition. But eventually, the rate's going to equalize. Because at this point, we started out with basically even. Oh, is that the right one? No, it's this one. We started off as basically even, but then where did they all end up? On this side. And the number there stayed basically the same, plus or minus 1. We have an 8, we have a 9, we have a 3, we have a 2. If we were to continue, I'd expect like an 8 and a 3, or a 9 and a 2, maybe even a 10 and a 1 for a moment because they're individual. But we have a huge advantage on this side that's sending them back. So at this point, what is the rate of the volleyballs going back and forth compared to each other? So what is the rate of the forward volleyballs and the backwards volleyballs?
Forward ball must be a lot less.
Pardon?
Like when you throwing forward would be a lot less because we're closer. So
You are closer. So at the beginning, the ones that closer, like they're really close. They can throw it really quickly. They probably threw like 6. They're further away. Maybe they missed a couple shots. They threw it 5. But over time, where did they end up? On the farther side. And so this side throws some. Put a number there, 3. I don't know. How many would they be throwing back? 3. Because at some point, This side that has that huge advantage runs out of ammunition. They can only throw back whatever they have. This side has lots of ammunition, but it's a really high hill to overcome. So they can only throw back so fast. So they eventually their rates become the same. The number of volleyballs passed per second didn't really change, no matter how I mixed you up. If I put everybody on one side and 3 people on the other side, it starts off with a huge volley, and then the rate is basically the same. You're there waiting for the other side to throw it to you if you're on the team with lots of people. And if you're on the team with few people, then you have lots of ammo, but not enough people, and you can only throw so fast. So they can only throw as fast as they're throwing back. Does that make sense? It's a huge, I go to the gym, I'm hoping this enters your mind. It makes sense even later on. Because I find it is helpful when you're doing these and you're looking at just math to think about what are the molecules doing? Because they're literally going back and forth. They go here, volleyballs. They go over the net. In our case, it makes an activated complex. And then it pops down the other side. And they just get thrown back and forth. These are two-way reactions. And if you're making AB at a certain rate, and you're making it really fast, eventually you're going to run out of reactants, and you can only make it as fast as it's being thrown back. So if this rate is really slow, then it's just going to accumulate here until this rate slows down. The number of people in this case is representing something like concentration. We had a high concentration of people on one side, they throw it all over, but now the balls are like all concentrated on the other side, so all the concentration is now over there. That is getting faster, well this is getting slower until they actually equalize. Is that making some sense? I've never done the demo with volleyballs before. So at the very least, I hope it was fun. But second, the really important part is, can we actually think about it in those terms? And if you have a reaction, so with an inhibitor, let's say we have a reaction like this. If I put in a poison, I had you sit on the floor, but I could have easily, if I could have raised the net. That is not a good curve. There you go. If you start and end at the beginning at the same side, and I just raise the net, would that change the ratio? No. Why not? Both sides are affected. If I added a catalyst, and this is the part I didn't want to do, the last thing I would have done would be to remove the net entirely. And then I'm like, well, if someone dies during a chemistry demo from a volleyball to the face, you're never getting to do this again. Would that have changed the ratio?
Yes.
Why?
Because this side has to still throw far.
But does it have to throw the same distance it did before?
No, but they're equal.
Well, because you just said that, like, when it was like this, it was normal, and when it was like this, it wouldn't affect it because it's higher for both of them. But if it's like this, it's lower for both of them. So even though, whatever the ratio is probably like, 6-2 or something. Like, it's still lopsided, but the lopsidedness stays the same when you raise and lower the middle because it's either harder for both sides or easier for both sides. The only thing that's going to change is the speed at which the volleyballs are going by, but the ratio will stay the same. Catalyst versus inhibitor. And then the analogy works if I start changing concentration. Changing concentration would be like I take everybody from one side, put them on the other side, and that can represent different levels or different concentrations. I can add more volleyballs, but ratios should roughly stay the same in that situation. So we did that last day, and okay. I'm not going to do any more because we have 20 seconds, and that is not a bad place to stop. Your quiz is on, and your test is on Wednesday. Test is on Wednesday, ABC.
Wait, I'm not here on Saturday.
Why?
I'm at SAT.
You're in what?
Oh, yeah.
SATs? So you're skipping class to write your SATs?
Yeah.
Your SATs are more important than class? I'm so disappointed. Are you also in SATs? Then you will miss the quiz day.